So I'm going to try this again. I'm going to try to set timer for 5 minutes.
Okay, 5 minutes and counting.
All right, so it's counting. So I'm going to cut myself. Let's get into it. So module 3, in a nutshell, is really about calculating expected value, weighted average, weighted mean, whatever you want to call it. Whatever you call it, the process to calculate it is effectively the same way. That goes from a frequency table to a relative frequency table to being able to generate weights or appropriate relative frequencies to calculate values. We can also see this represented in a histogram. Now, these histograms can either be actual frequencies or relative frequencies. It doesn't matter. Same thing with a bar chart, even if what you're going to see when we talk about grades here in a second, because you've got to be able to calculate your own grade. What we'll be able to see in a second is it doesn't matter if it's a bar chart or a histogram. Frequency versus relative frequency still provides you the same information. So let me share my screen. So first of all, if you're going to try to calculate your grade for this particular class, you have to realize that there's a number of different things which go into your grade. There are 5 assessments. 5 assessments. Would not autocomplete assessment for me. There's your homework grade, there's your participation grade, there's your quiz grades, there's your midterm grades, and there's your final grades. Now, each of these has different weights associated with them because your homeworks is worth 10% of your grade, your participation is worth 20%, your quiz grade is worth 20, your midterm is worth 20, and your final is worth 30. These are all either weights or relative frequency. Now, this is the symbol that we tend to use, but sometimes these can be called weights. It's frequency over total sum. In the case of your quiz grade and your homework grade, you've actually got 10 homework assignments. So this ends up being the average of your 10 homework assignments. And as far as your quizzes go, you have 4. So it's the average of your 4 quizzes. No assignments are dropped. No assignments are dropped. Now, whether we call it the weight or P of X, probability, proportion, percent, relative frequency, when we think about calculating a grade, it's really a weighted average. So depending on what you get, homeworks are pretty easy because they give you the answers. Let's say you get a 95. Participation, you just got to show up, but 90 tends to be a little bit above what the average is, although it's not normally distributed. Quiz scores tend to be pretty good because I give you the practice quizzes ahead of time. Midterm tends to pose a challenge because people think they're more prepared than they are. You have to understand the midterm and the final exam are tougher. So those grades tend to be harder, but then the final exam, maybe you rebound a little bit. Note that your assessment for some of these things tends to be, these are averages based on my experience in teaching this course for a couple of years. Those numbers are based on history, and they do represent and reflect how the student body tends to think about these things in general. Now, if we turn this into a table, Control-T, table, that's not what I want for my table. This is what I want for my table. Thank you. We can see that the sum of all those x's is 435. And if we take 435 divided by 5, we get 87. This is not your average grade because your homework grades are worth less than your final exam grades. It's important that we take x times P of x. Now, again, sometimes this looks like if we're talking about a weighted average, it ends up being your being the x times its weight. But either x times P of x or x times x, not P90x, is what you're after. So we take x times P of x. I said x times P of x. And it does that for all of them. All equals auto sum. As you see, 86 is your actual average, your course grade, rather than 87 because your final exam is worth a little bit more and you did a little worse than you did on your homework grades there. Another thing that we might see from time to time, oh gosh, this is going to run longer than 5 minutes. Shoot. Oh, well. Looks like I'm already breaking the fourth wall on you on there. Another way that we can think about this is we think about expected value. I'm going to follow the same process, but I want to illustrate it with just a couple of different scenarios. One of the scenarios is, let's say there's a game. And the game is I have these 3 sheets of paper. And depending on the sheet of paper you draw, you may win or lose a certain amount of money. For these 3 sheets of paper drawn at random, maybe you win $5. Maybe you win $5. Maybe you win $5. This is a really great game. all three of these tickets say you win $5. I have some other tickets which may come into the game a little bit later. I have a lose $20, I have a no pain, no gain, no money, and I have a lose $1. But for now, the game is based on there are 3 tickets. You select one at random, and that's what you get. Well, if you only have, yeah, I got it. I'm out of time. Maybe these should be in 10 minutes, not 5 minutes. I don't know. If you play this game, the original game, there were 3 possibilities. These are potential outcomes. You can win $5, win $5, or win $5. These are all the 3 possibilities, and if you select one of these at random, well, I think what you would get is probably a win of $5. So if I take the average of these 5 outcomes, I again get $5 because the value I expect to get is the same thing as the weighted average. Let's take a look at this another way. Potential outcomes, which we call X. And then there's a frequency that these things can happen. So if the outcome is a $5 win, sometimes written as $5, there are 3 possibilities of that. The probability, 3 occurrences of that. The probability of selecting from these 3 would be 3 divided by the total number of tickets, which is 3. To be fair, let's say this is the sum. And this is my fat fingers not being able to type. This is the sum. So the probability, and this is pretty trivial, the probability of drawing a win $5 ticket, if there are 3 win $5 tickets and nothing else, is 1. That's the probability of winning this game. But now, let's see what happens if I introduce one of these tickets where, let's say you could also win $1. It doesn't need to be bold. Doesn't need to be underlined. All I want is to introduce one possibility here, and that is that you could possibly win $1. Now there are 4 possible outcomes. There's a 3 in 4 chance. My fingers are too fat. There's a 3 in 4 chance that you win $5. There is a 1 in 4 chance that you win $1. If we follow the same procedure that we just did in order to calculate your grade by generating a table, saying this should be a sum, all equals auto sum, do x times p of x, and take the sum, the amount of money I can expect to win playing this game is now $2.50. It's no longer $5 because there's a small possibility that I might only win $1. So this expected value is the same, calculated the same way that you would calculate a particular grade. It's by taking a weighted average. This is really the crux and what's crucial. This is really what's crucial about Module 3. There's one other thing, in spite of the fact that I have all these other types of wins and tickets and things that can happen. One other thing I'd like to illustrate, which comes out of Module 3, and that has to do with the concept, whether or not we calculate it, the concept of variance or standard deviation or dispersion. When it comes to the game where I have 3 tickets and they're all identical, there is no variety, there is no variance, everything is the same. The opposite of variety is consistency. And if we measured the variance or the standard deviation or the range, any measure of dispersion of playing this particular game, the value would be 0. 0 has a meaning. There is no variance, 0 variance, no variety. But as soon as I introduce some sort of variety, however little it might be, or a lot, if I introduce a little variety, then I've increased the variance by just a little. If I start to add more and more potential outcomes to this experiment, the number, the value of the variance, or the standard deviation, or even the range, highest possible, lowest possible. All measures of dispersion start to increase the actual number, the value. And that's what I mean in both the meaning of the variance going up or the value of the quantitative number you calculate. Looks like this. When we played this game originally, that was supposed to be 0, not 1, whatever, 0. Hey, the expected value should go probably down a little bit. You know what I did here? I did this wrong. This is supposed to be x times p of x. 375. I knew that number looked a little small. Oh, no. Oh, no. I did something wrong, so I have to wear the doing something wrong hat. My bad. The expected value should be $3.75. I got a little excited about calculating some things, trying to get it in under 5 minutes. This is never going to work. Maybe it will at some point. The variance of these three values is 0. The standard deviation of these three values is 0. There's no variety, so the value is 0. But as soon as I introduce some other value, the variance does increase. The standard deviation does increase. This is just the square root of the variance. The standard deviation is just the square root of the variance. But it went from when I was just looking at the standard deviation or the variance of those three things, which are the same, there's no variety, so it's 0. But as we start to increase dispersion, start to say, you know what, there's some other things going on, that value of 95 or the corresponding standard deviation, these values of 9.7 or 95 and their corresponding, all of these are all variances and all of these are standard deviations. Those values go up as there's more variety. And that's really what the metric of standard deviation means. But I got wearing the Cleveland Browns hat, doing things wrong hat. There's one more thing perhaps maybe worth pointing out. In those three cases where I calculated the variance and the standard deviation, I did do one more thing wrong. When you calculate variance or standard deviation on small sample sizes, regardless of whether or not it's everything that you have, you should be using the sample standard deviation or the sample variance formula to calculate those values. But in my haste to calculate them quickly, and influenced perhaps by the doing things wrong hat, I use the population variance and standard deviation functions. Those of you with access to the module should make sure you take a look at the differences between those two things. Conceptually, they still talk about the concept of dispersion. So expected value, weighted average, those are the same things effectively. And dispersion metrics, how you understand them conceptually. Those are the big points that I couldn't get in under 5 minutes for Module 3.